Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, I'm going to go through the notes that I covered with my students on characteristics of functions. It's actually the first section in our polynomial unit. So basically what I'm just going to run through my lesson because I need to provide the answers to my students. So therefore, you can come along and join with me as far as how I instructed. I'll highlight some points. I'll talk my way through my answers, or at least my work, and hopefully that can be beneficial to you. So what I kind of went through my students, I'm going to talk to them about what makes polynomials unique, to talk about end behavior, and how to graph polynomials. So I kind of started off this with a little question, had the students, kind of read this, and, kind of made them think of like, do you get a speeding ticket, if you go through, if the speed limit is 60 miles per hour and you enter the tunnel at 45 miles per hour, exit it at 45 miles per hour, but it only takes you 3 miles and 30 minutes to, 3 minutes to travel 3 miles. And the one thing that we came up with as a students was, yeah, you should get it because, we're not going to get into like the average value theorem or anything like that as far as in calculus. But, if you're just thinking of your speed and your time, right? Well, not so much the, how fast you're going. So if you're starting at 45 miles per hour, right, and you exit at 45 miles per hour, obviously to travel, a mile in 3 minutes or in 1 minute would be 60 miles per hour. So now typically, obviously when you're driving a car, the one thing I was trying to tell the students is, obviously there's not like a teleportation device or something like that. Like if this is saying here's the speed limit or here's 45, and here's, 60 miles per hour, and this wouldn't be in time. Let's just put this as our distance. Right? And let's say here's the tunnel and then there's the tunnel, right? So you're going at 45 miles per hour. Obviously, you can't just jump up to 60 miles per hour during that time and then jump back down and exit the tunnel. Right? So if you have the speed versus the distance, that doesn't work like that. That's not how the speed of a car works. So what what we can do to represent that is, typically somebody's going to have to go really, really fast, and then they'll slow back down once they see the copper, they know they're going to exit or something, and then they'll be going down. But either way, they broke the 60 mile per hour. They had to have, as you accelerate, you had to pass that. And that's something that we're just going to kind of want the students to kind of talk about as far as the path of a car, as you're accelerating and decelerating. You can't do this, or you can't do a teleportation device, going through there. But then we'll talk about that continuity here in a second. But let's go ahead and get into the next portion, which was really looking at the graphs of factors. So what we're going to do is we're just going to graphs of polynomials. So I asked them to kind of compare the equations of these polynomials. Things we're going to look at is how many x-intercepts are, where the x-intercepts are located, how many points, I forgot to delete that, oops, how many points of extrema are there, what is the end behavior, and what is the highest power of each equation, and is there any connections between there? So let's go ahead and take a look. Okay, so looking at this with the students, I kind of went through this and we said, all right, let's just kind of get into some ideas here. Now, obviously here we have, two factors. We have y equals x times x minus 1. Now, if we were to multiply that, that would give us y equals x squared minus x. So therefore, hopefully we recognize that as a quadratic equation. And as we kind of zoom in, you recognize that the x-intercepts occur at 0, 0 and 1, 0, right? The next one, if we were to multiply those all out, you think, x times x minus 1 and then times that by x plus 2, hopefully you'd recognize that's going to give us a cubic function, right? Something to the third power. So we go ahead and click on that and we see, oh, kind of interesting here. Now let's kind of stop at this point and kind of recognize some things. Again, they share the same x-intercepts at 0 and 1. And notice that they also share the x and the x minus 1, right? The x-intercept here at 0, and then here's the x-intercept at 1. And then this represents an x-intercept at -2. Now, it's interesting why those values work. And again, if you plug those numbers back in, the x values, -2, 1, or 0, all those values make each factor 0, which then again makes the whole polynomial 0, which is very, very important for a later definition. Or you could also think about they all make the equation 0, which is the y value, right? Because those are x-intercepts. Y is always equal to 0 for the x-intercepts. Now, the last thing I want to kind of cover, at least you to kind of recognize, is this is an x squared. You can see that the end behavior of this is to the rises to the left and rises to the right. Whereas the end behavior of this, cubic function is falls to the left and falls to the right. So the end behavior for x cubed is, going in opposite directions, and the end behavior for the x squared is going in the same direction. Now, following that kind of idea, if we were to kind of think about multiplying this, hopefully you recognize there's 4 factors. So therefore, we can probably make the assumption then that's going to be an x to the 4th. We can recognize that the factors are going to be at 0, or I'm sorry, the x-intercepts will be at 0, 1, -2, and 3. So let's go and graph that and see. And you can see the x-intercepts are exactly where we thought they are going to be. This is indeed to the 4th power if you multiply it out, but you can see that the end behavior here is falling down to the left and falling to the right, which is very similar to this end behavior, right? The difference is, though, one is going up and up, one's going down and down. The reason why they're different is that negative right there. You can see, obviously, the negative is reflecting it about the x-axis, something that will become very important here later. And then we looked at this one. Hopefully you recognize this would be 1, 2, 3, 4, 5. This is going to be to a polynomial to the 5th power. It should have the same end behavior, x-intercepts at 0, 1, -2, 3, and -4. However, it's not going to have the same end behavior as this polynomial, because this one was positive, so that fell to the left and rose to the right. This one would be a reflection, which would be rise to the left and rise to the right, which if you kind of zoom out here, you can see that's exactly what is going on. I kind of did a crazy polynomial here, but you can see it rises to the left and falls to the right. Okay, so now let's go and get into some more examples. Okay, so we did pretty good on connecting everything as far as the equations. I think as far as some connections, though, that we can kind of play with is that, let's just kind of zoom. The number of x-intercepts the number of x-intercepts was the same number of factors. The x-intercepts were located at the values that made each factor 0. The number of points of extrema, I actually forgot to go ahead and do that, so I'll make sure I do that on the next one. But if you actually kind of remember or look back at those graphs or back in the video, you'll notice that the extrema, the absolute maximums, relative maximums, those are always one less than the extrema, or one less than the power. We talked about the end behavior. The highest power was the same thing as the number of factors. And was there any connections between these given equations? Yeah, we talked about the ones that had a even degree, x squared or x to the 4th, had the same end behavior, whereas the ones that had an odd, x cubed and x to the 5th, those had similar end behaviors. All right, and then I'd like to just kind of do a quick little review with the students as far as like a line. Actually, I forgot to write these in there, so I'm going to go ahead and do that. So this is our linear equation, so y equals x. This is our quadratic, y equals x squared. This is y equals x cubed. So most students are familiar with those three. But then I wanted to introduce them to some other parent graphs. Y equals x to the 4th, y equals x to the 5th, and y equals x to the 6th. And the reason why I wanted to bring this up is there's a couple important things that are going on here. We talked about the power was the same number as the factors, right? If it had 2 factors, it was to the 2nd power. If it had, 3 factors, it was raised to the 3rd power. And also, well, not even the factors, but the number of x-intercepts, right? The number of x-intercepts was the same as the potential power. But here you recognize all of these only have 1 x-intercept. So even though this is to the 5th power, there's only 1 x-intercept, right? And that's kind of interesting because our idea of thinking the number of x-intercepts is the same as the power is not necessarily true, right? You can see that doesn't work for any of these. There's only 1 x-intercept for all of these, and except for the first example, they all have a power larger than 1. So let's go ahead and make some sense of these by looking at some different equations. So we're going to look at these and we're going to kind of talk about the same exact idea as far as as far as talking about the end behavior and the number of x-intercepts. Okay, so just real quick here, I did want to kind of go back to the extrema portion. So if you remember x minus 1, that was one that we talked about. You can see there's only 1 extrema, right? So this had 2 factors, 2 x-intercepts, and we knew this was a quadratic, and there was only 1 part of extrema. The next one is if we kind of did the next example, y equals, x times x minus 1 times x plus 2. Here you can see that, again, now this is a cubic, right? So we multiply 3 factors. That means there's 3 x-intercepts, and there was 2 extrema. So one thing you can recognize was the number of extrema was always less than the number of x-intercepts, or the power. But that is not always true, as you're going to see in these examples. So let's take a look at the first one. If you take a look at this first one, you can see that there's only 2 factors. So we can assume there's only going to be 2 x-intercepts. Therefore, this should be a quadratic. But if you kind of think about multiplying this out, you recognize it's not going to be a quadratic. And you're right, it's actually a cubic function. And again, you could see that because x minus 1 is repeated, right? That's the same thing as writing y equals x times x minus 1 times x minus, minus 1 times x minus 1. Right? So this is so when we raise something to a power, it's repetition. We're repeating it. But if you look at that graph, the red graph and the green graph are exactly the same. Okay? This is our preferred notation, and we'll talk about this notation a little bit more coming up. But I just want you to see why this comes out to be x cubed, because if you were to multiply that, that's going to give you squared, a power, a polynomial to the second power, and then you multiply by another x, and then give you x cubed. There's also something that's very important that's happening, is the behavior of my x-intercepts. I have 2 x-intercepts, right? But the behavior of these x-intercepts is different than in the last example. This x-intercept that got repeated, now it doesn't look like it crossed it looks like it bounces. And not only does it look like it bounces, it looks like it bounces like a quadratic, which might make a little sense to you because this is x minus 1 to the second power, which would kind of represent it like to the second power. So this is to the third power. Again, we have 2 pieces of extrema, which is 1 less than the power. However, to the third power does not have 3 x-intercepts anymore, right? So that is no longer something that we're going to be able to rely on, all right? So now let's go and take a look at this one. Well, if we were to multiply this out, you can see this is going to be an x squared. This would be raised to the third power, or this would be 3x minus 1s, and this would be an x plus 2. So if you were to multiply that out, that'd be an x squared times x to the third times x. That's going to give you an x to the 6th power. However, there's only 3 x-intercepts. And you can see exactly how these x-intercepts lay. We have -2, 0, and 1. Now again, what I want to kind of bring your attention to is not only these x-intercepts, that even though there's 3 x-intercepts, this is actually to the 6th power. And you can make sure of that because of the end behavior. But in addition to that, look at the behavior of how they cross the x-axis. This crosses like a line, this bounces like a parabola, and this crosses like an S-curve. It's kind of like a little S-curvy, right? Which kind of makes sense. If you look at the zero, if you look at like where the zeros come from, which factor they came from, the x plus 2, the -2 comes from here, which is raised to the first power, so it crosses like a line. The x plus 1 comes from this factor, which bounces like an S-curve, or crosses like an S-curve, and here you have an x squared that's going to bounce like a parabola. So again, you can kind of see the same patterns are starting to take shape. Here, we could see that the highest power is going to be x to the 4th, x to the 3rd, x to the 3rd, so that'd be 6, 10, and then be x to the 11th. But there's not going to be 11 x-intercepts. There's only going to be 4 x-intercepts. And you can see again, they take shape of like a cubic, crosses like a cubic, crosses like a cubic, crosses like a line. And this one bounces like a quartic, right? Because it's raised to the 4th power. So the behavior of the x-intercepts is based on that power. Something that's very interesting we'll talk about here in a second. But again, the main thing I wanted you to see from this is, let's at least look for this one, is the number of pieces of extrema is no longer 1 less than the power of your polynomial. So here I have 1, 2, 3 parts of extrema. But again, remember, this is raised to the 6th power. I don't have 5 pieces of extrema. So the fact that the highest power of your polynomial is equal to the number of x-intercepts is no longer true. The fact, and that was shown in the first example. The fact that the number of extrema, it was always 1 less than that highest power of the polynomial, is also no longer true. And again, those are 2 things we're going to explore here coming up. But I wanted students to see these, and also so they can quickly identify the zeros here. 0, 1, -2, 3, -4. Also, make a connection with not only the numbers, because like the numbers tell you how they behave, right? Like what type of graph they cross like, but they also tell you if they bounce or they cross. Notice if they're even, they bounce. If they odd, they're going to cross, right? And you can see that each one of these, each of these x-intercepts, when their factors raised to an even power, they bounce. -2 and +3, right? And 0. And then at 1 is the only 1 and -4. You can see those are the only two. Where is it? 1 and -4. Those are the only two that are actually raised to an odd power. So that's what I wanted students to take away from this. And we spent a lot of time going through this so they can really understand what's happening. Okay, so now kind of going back in with the end of behavior, make sure we got with the discussion. We talked about the x-intercepts. Again, the x-intercepts are located at the factors. We have the same points of extrema, but it's not the same as the first example. The end behavior was the same thing. It didn't matter if it was raised to the 12th power or to the 4th power. If it had an even highest power, the end behavior was going to all be the same. So that's not something I talked about, but what you notice is the end behavior, and we'll talk about this a little bit more as we get to it, that the end behavior was really kind of the same going up and up, if the power was even or odd. All right, so then I kind of gave students, really like the basic definition of a polynomial, but really what I wanted students to understand of a polynomial is basically it's a sum of monomials. And so main important thing is it's sum of monomials and that n needs to be an integer. So we do not want n to be negative, right? Because if I have x to the negative n, well, that means it's going to be a reciprocal function. Or if I had x to the, fractional n, so like 1 over n, well, then that means it's going to be a root, and we don't want that either. So these are examples of not polynomials. But there are some really important things. When we're writing polynomials, all right, we want to write them in descending order. That means the highest power first. So we have an exponent x to the n represents our degree, and a represents our leading coefficient. So I usually just use LC to represent that as a leading coefficient. But those are going to be some really, really important parts. The rest of the polynomial we don't really care about, at least in this chapter, at least in this section, because it's not going to be really much of use to us, which I'll kind of explain as I do some problems. So again, polynomials are going to be smooth and continuous. There's not going to be any sharp turns or points of discontinuity, so we're not going to have to worry about domain. Domain is going to be always all real numbers. They continue indefinitely. That means they're always going to have end behavior. They're not going to repeat or bounce or stop. And then polynomials will have at most, that's really important, it's at most n minus 1 extrema and at most n, I'm going to change this to x-intercepts just because I didn't introduce the word zeros yet. So at most n x-intercepts in positive or negative direction. Yeah, so it's going to be n positive without bound. So what that means is like if you have a quadratic, right? The maximum, and this makes sense hopefully to most students that, we know quadratic. If you remember from the quadratic formula, there's only 0, 1, or 2 solutions, right? You couldn't have 3 solutions or 4 solutions. So that's what this is saying, because a quadratic is a polynomial, that you have to have at most that whatever the power is, that most x-intercepts or solutions. And at most n minus 1 extrema. A quadratic, which is raised to the second power, only has one vertex, right? That's the extrema of a quadratic. It doesn't make sense for a quadratic to have 2, right? 2 extrema. It's only going to have 1. And again, as I showed though, just because you have something to the 7th power doesn't mean that it has 7 x-intercepts or that it has 6 pieces of extrema. Those are just the maximum number, because what we found is we can write polynomials in that second example as a repetition with, right, as a repeated repeated factor x-intercepts. All right, so then I had to kind of cover some problems with students just to make sure they understood, x and y intercepts. The x-intercept is the x value where the graph crosses the x-axis when y equals 0. And the y-intercept is the y value where the graph crosses the when x is equal to 0. And again, like kind of made a quick little thing. If I had like y equals x minus 1 times x plus 2. And I said, guys, like where do you find the x-intercept? If I want to say what is the x-axis, you're just going to replace 0 with y. 0 equals x minus 1 times x plus 2. And they say, oh, now I have a product equal to 0. Now I can apply the 0 product property. And now I can go ahead and solve. So A lot of students don't have a problem identifying the x and y intercepts on a graph, but it's very important, which I already kind of like explained, those x-intercepts, y is equal to 0. For the y-intercept, x is equal to 0. So algebraically, if you need to figure out what is the x and the y-intercept, so this is the x-intercept, to find the y-intercept of a random equation, you're going to plug 0 in for x. Okay? And we'll kind of come back to that in a second. Actually, right now. So the next one is the zeros of the function are the x values that make f of x equal to true. So the zero is a real zero is a x-intercept of the graph f of x. So this is really important. So I just did, one where's y. So what if I had f of x equals x minus 1 times x plus 2? What if I gave you that and I said find the zeros? Well, again, then you're going to find the zeros as basically the values that make, when f of x is equal to 0, that make that equation true. Now, obviously, we've already figured out the answers here are x equals 1 and x equals negative 2. So the real zeros are the same thing as the x-intercepts, right? However, notice I'm using the word real because we're also going to get into non-real zeros, but that's going to be later coming up. All right, so that repetition that we went ahead and solved was the multiplicity, right? Or what we call multiplicity. And that just basically means you're going to be dealing with a factor or a zero that's going to be repeated. So the multiplicity of a zero determines the behavior of that real zero. So if you know the power of that factor, and you know what that graph looks like squared, cubic, then that's the behavior that the x-intercept is going to have where it crosses. However, it's very important that the multiplicity can only be found when you have something that's a linear factor. Okay, so that's going to be x minus c raised to the m. X is raised to the first power. Okay, so one of my common things is if you have x squared minus 4, that's not a linear factor, right? So you don't say that this has a 0 at 4. If this was like this here, so example, the multiplicity is going to be a linear factor. The main important thing, though, the 0 is basically at c, right? Because then again, notice the form x minus c raised to the m. But notice here the multiplicity is, if I said, a 0 of 4 and a multiplicity of 2, that is the correct way. It's x minus c. So c is 4, your 0, raised to the second power. Do not get that confused with x squared minus 4 as a 0 of 4 and 2, because if you were to factor that out, you'd actually get x minus 2 times x plus 2. Okay? And a lot of times I just took a quick little look at the graphs to kind of, bring this home to the students. Okay, so obviously we kind of talked about this one. We already know the x-intercepts are, in this case, are going to be at negative 1 and 2. These are a little bit different, actually, than the example I did. Here, I'll actually just, let me change this. Minus, plus. So therefore, it's the same one as I did in my example. Okay, so the main important thing that I want to get to see is, these all have the same 0, or they all have the same x-intercept or zeros. The only thing that's going to change is now their behavior or how they repeat, right? Obviously, this is to the second power, and this one now is to the fifth power. So it's going to have a different end behavior, and the behavior of these zeros is going to be different. You can see this now crosses like a cubic at negative 2, and it bounces like a quadratic at 1, right? If I go to here, now again, this is going to be an odd, so it's going to have the same end behavior as the blue, but again, the behavior is going to be different. That was actually, how did that switch? That's not supposed to be like that. That's supposed to be a 5. And that's supposed to be a 4. Okay, so now again, you can see that the 1, now that has an odd behavior, or that has a end behavior like the polynomial to the fifth power, and this has one like a polynomial to the fourth power. So you can see how that power, it doesn't change the x-intercepts, right? But the power changes the behavior. And again, we can also we can also summarize this by if they're raised to the odd power, they're going to cross. If they're raised to an even power, they bounce. And again, you can see in all these instances how that is the case. And the last one that we have to go with is just going to be linear factorization. Basically, it just means when a polynomial is written in factored form. So for instance, like, y equals x minus 1 times x plus 2 is called linear factorization. And that's important because when you have something written as a product of its factors in linear factors, then you can identify the zeros, you can identify the multiplicity, right? This is not x squared, minus x minus 2. That is not in linear factorization form. We can't quickly identify the zeros in the polynomials. And also, one last one is, remember, don't get confused with this, x minus 1, squared plus 1. Like, even though that's written as a binomial, right, square we have like this, that is not in linear factorized form, only as a product. All the factors are multiplied together. Okay, so just make sure you know the difference of when something's written as linear factorization compared to like your standard or your vertex form. All right, so the next one we worked on was the leading coefficient test. Basically, I kind of gave students, kind of some notes, but really I just wanted students to really kind of recognize the main important things here for the end behavior test. Really the main thing is, rather than trying to understand or memorize all these things, it's just to look at like the graphs of things that you know. So from the beginning, we've understood that there's the only difference between our polynomials as far as end behavior goes is if the highest power, which we now know is called the degree, is either even or it's odd. And if the leading coefficient, the number in front, is either going to be positive or negative. So the way that I remember this is I don't remember all of this or memorize all of this stuff. I go ahead and look at this little 4 quadrants here. And I recognize that the quadratic, I have the quadratic, memorized, y equals x squared. And I know that opens up and up. And therefore, if it's a negative x squared, I know it's going to open down and down, okay? The next thing is if I have the odd behavior, doesn't matter if it's x or x cubed, I know that's going to be falls to the left, rise to the right. But if that's a negative x cubed, then it's going to rise to the left and rise to the right. Because again, remember the negative is reflecting it about the x-axis. So I keep things pretty algebra 2 here, especially when we just go ahead and look at the graphs. So let's go and take a look at the graphs here. You can see these changes. So, first we looked at the quadratic and say, oh, okay, I understand that. Now again, the point is, if you remember what the quadratic is, you know that has an even degree and an odd power. It doesn't matter what the polynomial is. If the degree is even and the leading coefficient is positive, it's going to have the same end behavior. Even if it's odd, if it's even and odd, and it doesn't matter what the rest of the polynomial is, as long as the highest power is even, the leading coefficient is positive, it's going to have the same odd behavior. Even if the leading coefficient is a fraction and the degree is 8, doesn't matter, it's going to have the same end behavior. Even if this was, I couldn't even remember this, but even if it was the square root of a number, you're still going to have the same end behavior. So it doesn't matter what those numbers are. We're only looking at the degree, is it even or odd, and the leading coefficient being positive or negative. Because obviously if it's negative, that's going to change. That's going to change the end behavior here, obviously to flip it around, right? So it doesn't matter what the number is as far as, its value, but it does matter if it's positive or negative. And that's the same thing for, odd. It doesn't matter if it's x to the first or x to the 199th. And you can see that these exactly have the exact same end behavior. They don't follow the exact same rate, but they have the same end behavior. Lastly, the only thing that we want to talk about is instead of using our notation as like falls left, rises right, I started students using some new notation. So, I basically mean the arrow means approach. And so therefore, as I say, as x approaches infinity, that's basically another way of saying as x moves to the right, or as you're moving to the right. So that's what I have here. It lead a little bit over in this, kind of skill from there. But that's one thing I wanted students to kind of get used to was this new kind of notation. And we did this for all of them. And obviously, as I do my examples, we'll work through it. So then we went into determine the end behavior. So determine the end behavior and write in math notation. So when we're doing a problem like this, main thing we want to do is make sure that we understand the highest power, that degree. Like we need to figure out what is our a x to the n. We don't care about anything else. So all I'm going to do in this case is I'm going to rearrange this. So this is a negative 2x plus 1 squared times an x plus 1. Now, there are some tricks and tips that students will start to follow, but I recommend that you just kind of take it slow for a second to really understand what you're doing, because a lot of these negatives will get a lot of students. So here I have 1/2 x, right? If I was to multiply negative 2x plus 1, that would give me a positive 4x squared. Now, I could figure out the rest of it, but I don't want to. So I'm just going to write ... x plus 1 squared is going to give me a leading term of x squared. Again, you could multiply it out, but it's just a waste of time because we only care about that first term. Now, if I was to multiply, let's do these two binomials, 4x squared times x squared, that would give me a 4x to the 4th. And again, don't know what the rest of it is. And then I'd get 1/2, so now 1/2 times 4, 1/2 x times 4 to the x to the 4th is just going to give me 2 x to the 5th. ... Okay? Now, let's figure out what this end behavior is. So the end behavior, again, is the same thing. This is the same end behavior as y is equal to x. The same end behavior. So I know hopefully from there I can say, oh, okay, that falls to the left and rises to the right. Now, if I'm going to use math notation, basically here what I'm going to do is going to say, well, if I need to say falls to the left, I'm going to say as x approaches negative infinity. That basically says x is to the left and right, right? So as x goes to the left, f of x, which is my y value, is going to approach negative infinity. Because if it's approaching infinity, it's going up. If it's approaching negative infinity, it's going to go down. And then if I want to say something's rising to the right, I'd say as x approaches infinity, f of x approaches negative. I'm sorry, it needs to rise, right? So it needs to go as a positive infinity. All right, so that's basically what we kind of worked on with that. And then I kind of gave students, these kind of 4 questions to kind of work on. So the nice one here in the first example is, or these first example is that it's already in the form, right? So I have my degree is, 4, so I can say degree is 4, which is even. And my leading coefficient is -1. Sometimes it's nice to kind of go back and say, oh, I have an even degree and a negative leading coefficient. Therefore, this is going to fall left, fall right. So I'll write them so you can do the kind of transformations, falls left, and this is going to falls right. And then I'll do the math notation. So as x approaches negative infinity, f of x approaches negative infinity. As x approaches infinity, oops, no, don't want to do that. F of x approaches negative infinity. Okay, to the next one. Now this one gets a little tricky just because it's not in descending order. If you remember from the definition, you want to write things in descending order. Now I don't need to rewrite the whole polynomial. I just need to rewrite it so the highest power is first, right? And you can see that is x cubed. Make sure, though, you keep that -6 as the coefficient with that polynomial, okay? Obviously, that would be a mistake. You don't want to take like a +6 because then you get the end behavior wrong. So this one is a negative leading coefficient and a odd degree. So therefore, this is going to rise to the left and falls right. And again, if you want to check my answer, obviously you can always graph these, but I'm just doing those 4 quadrants in my head. That's what I kind of basically have memorized at this end. My main thing for a lot of students is making sure they understand, can do the math notation. So this would be as x approaches negative infinity, f of x approaches infinity because it's rising. And as x approaches positive infinity, f of x approaches negative infinity because it's falling. Now the next one I'm going to have to multiply out. So that's kind of what we looked at in the last one. So if we were to multiply these out, and again, I don't really like this x not in that order. So what I'm going to do is I'm just going to rearrange this so the x is written first. Okay, so what that tells me now is that's going to give me a negative x squared. So we've got to be careful with our negatives. So we have a negative 2x times a negative x squared, dot, 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 dot. Okay, now if I was to distribute that, I would get a y equals a positive 2x cubed. Okay, so therefore you can see that this is going to have a positive or a positive leading coefficient, which a lot of people get confused, and a odd degree. So therefore it's going to fall left and rise to the right. So as end behavior here, so falls to the left and rise to the right. So let's see, as x approaches negative infinity, that's going to the left. F of x approaches negative infinity. And then as x approaches in positive infinity, f of x approaches positive infinity. Okay, and last but not least is we have one more, which again, we're just going to want to see what the expansion is going to be here. So we have this number in front, which is the 1/4. That's not really changing anything with my end behavior, right? It's just a little fraction. If I had x minus 4 to the third, if I was going to multiply that 3 times by itself, my highest power would be x cubed. Then I have an x plus 1 or x plus 2. And then again, this one I have a 1 minus x squared. Now again, this is important. If you think about this as negative x plus 1 squared, negative x plus 1 times negative x plus 1 is going to give you a positive x squared. So since that negative is being raised to an even power, it actually turns it into a positive value. Now when I multiply all these out, you can see that you get 1/4. Let's see, this would be x to the third times x would be x to the fourth times x to the sixth. So a lot of students like to recognize that you can just add the exponents, right? 2 plus 1 plus 3 gives you 6. And really, a lot of times that works. My only problem that I have with students doing that is when you look at like an example like this, if you don't recognize, or even not an example like this, but if I was to change this to the third, this would now be a negative x cubed, and therefore the 1/4 would be negative. So as long as you're able to catch your negatives and understand that point, that's perfectly fine. I just caution a lot of students getting to that point of making that mistake. All right. So therefore, it's positive and it's even. So therefore, this is rises left and rises right. Okay, so therefore, as x approaches negative infinity, f of x approaches infinity, and as x approaches positive infinity, f of x approaches positive infinity. All right, so we're getting on to the last process here, which is graphing polynomials. So the process really to graph a polynomial is to, one, determine the end behavior by applying the leading coefficient test, which we just practiced. Determine all the real zeros, and which are, again, real zeros are the x-intercepts. So that means we need to replace f of x or y with 0 and to solve. We need to identify the multiplicity of each zero and graph. We need to apply them to each zero. I need to fix that. Then we need to sketch the graph from left to right by connecting zeros and the end behavior arrows. So, sketch the graph of the following polynomial. All right, first thing we need to do is just find end behavior. Now, recognize here, if we were to multiply that as what we get. So we have negative 3, x squared minus 1. And then in this case, if we were to multiply that out, that would give you a 4x squared. And again, we don't really care what the rest of this is at this point. Multiply this out here, I'm going to get a negative 12x to the fourth. Okay, now the only thing I know now is I'm not going to worry about math notation here. I know that this falls left and falls right. Okay, so if I'm going to graph this, I'm just going to put my two end behavior arrows like this. It needs to fall to the left and it needs to fall to the right. All right, the next thing is we need to find the zeros. So again, the zeros is going to be basically setting our equation equal to 0, right? You replace f of x or you replace y, with 0, and now you're going to solve, because basically finding these zeros or finding the x-intercepts is the same thing as finding the real zeros. Now, the nice thing about, again, factored form is we have a product of factors equal to 0. So since we have a product of factors equaling to 0, we can apply the zero product property. And I always joke with the students, I made the same mistake with each of them. I made the mistake on purpose, by the way. But I wanted to show them, go through a common mistake of students taking that negative 3 and setting that equal to 0 as well. Right? And again, if you look back into like our Desmos, 3 is not an x-intercept. The x-intercept only came from the factors, right? As an x minus c form. There's no x with the negative 3. Negative 3 is not a factor. And that's actually one thing I work in the Desmos I forgot to add in because I was using the equation. But like if you add a number in there, that doesn't like change the 0. That just it stretches or compresses the graph, right? That negative is just a reflection. That doesn't add a 0 here. And this doesn't make any sense at all either. Negative 3 equals 0. Like it doesn't even make any conceptual sense. So what do we do with this? Well, we can just divide it out, right? You can just divide out a negative 3 on both sides. And therefore now you don't need it anymore, right? It's been divided out. So let's go ahead and solve for these. So a lot of times, we'll add the 1 to both sides. And then a lot of students will make, again, the grave mistake of when they introduce the square root of not including plus or minus 1. The next mistake a lot of students will do is they will, use their inverse operations before undoing the square root. So remember, we got to get rid of the squaring first before we can undo, the addition and the multiplication. So we take the square root of both sides. We don't need to do plus or minus with 0 because 0 is not positive or negative. So equals 0, and then if I use my inverse operations, x is equal to 3/2. All right, so I have, negative 1, positive 1, and then we have 3/2. All right, so that's an x-intercept, that's an x-intercept, and then that's, let's do that. And then that's an x-intercept. That really should be like 2. So we know those are our 3 x-intercepts. Now we got to go and look at our multiplicity. So we got to look at the powers. Now again, to look at the powers, we got to look at this in linear factored form. This is not in linear factor form. Not every factor is in linear form. This is negative 3 times x minus 1 times x plus 1, right? If you were to factor that down, that would give you x squared minus 1, x squared plus 1. Then we have the 2x minus 3 squared. So hopefully you can see that, again, the zeros are produced from the factors x equals 1, x equals negative 1, and x equals 3/2. So at the factor x equals 1, you can see that that has a power of 1. So it's going to cross like a line. At x equals, for the 0, negative 1, again, that factor has a power of 1, so that's going to cross like a line. And then for the factor x equals, or the 0, x equals 3/2, you can see that has a power of 2. So that's going to bounce like a parabola. The problem is we don't really know exactly how that's going to bounce up or down. But now we have really all the information we need. We have the end behavior, we have the zeros, and we have the multiplicity. So now all we're going to do is just going to connect. Let me just do this a different color here. And it's not a perfect graph, but you can see how this exactly kind of works for each one of those. All right. One thing that was just kind of messing with me, I just got to go ahead and complete this. Again, like this negative 3, just real quick, is bothering me. Because again, if I knew, let's kind of go back up to this. Linear factorization, product of your factors. X-intercepts. Is this the X? No, where's the X-intercept? The zeros, the X-intercepts, yeah. Let's just do it from here. We know that the zeros are y, like if I did f of x is equal to 3 times x minus 1 times x plus 2. The zeros are still going to be, like you divide out the 3 first. Like that's still going to give you x equals 1 and x equals negative 2. When you look at that graph, all that 3 does is that just that just stretches the graph, right? It's a vertical stretch. It's not a 0. I had to that is something I went over with my classes that I just wanted to kind of cover. Okay, so now let's get on to the sketching of the graph. So here's kind of the 4 examples that I wanted to work in with my students in class. So again, to kind of follow through that process is you're just going to want to, first thing is identify obviously the leading coefficient. So if you were to multiply all of this out, or I'm sorry, the end behavior, this would be a 4x squared, times x plus 3 times, let's see, x plus 2 cubed would be an x cubed, right? Dot, dot, dot. So if you were to multiply all of that out, I would get a 4x to the 6th. Okay, so there I can identify that my graph is going to rise to the left and rise to the right. So as far as sketching the graph goes, I'm just going to draw a little graph that's going to have arrows rising to the left and rising to the right. Now again, the next step is to find the zeros. So to find the zeros, remember you're just going to replace f of x with 0. And so therefore, you just rewrite the expression. Now I'm going to save some time on the rest of the problems because remember we're setting f(x) equal to 0. Well, now you have a product of factors equal to 0, so you can apply the 0 product property. Okay, and by applying a 0 product property, now we're just going to go ahead and solve each one individually. So this is going to give me x is equal to 0, x equal to -3, and x is equal to -2. Now again, we want to go ahead and list those as real zeros, but they're also real x-intercepts. So therefore we have 0, we have -3, and we have -2. All right, so now we got to look at the multiplicity. What is the power of each one of these factors? Well, at 0, we have a multiplicity that is 2. So therefore it's even. That means it's going to bounce. It's going to either bounce up or it's going to bounce down. At -3, we can see that that has a odd multiplicity of 1. So we can just say the multiplicity is 1, and that means it's going to cross, it's going to cross like a line. Now, in the same respect, at -2, I wrote that as cubed. That's why I was getting confused. At x plus 2, that's cubic, right? So again, now you could write that as an S-curve. You don't know is though going to like S-curve like this, or is it going to S-curve like that? So a lot of times we just go by, well, it's odd, so we know it's going to cross. And now that we have this form, just go ahead and connect them. So we're just going to connect from here to here to here and there, and then there you go, okay? And that's basically the same routine that we're going to follow for the rest of these. Rather than rewriting it as the zero, rather than rewriting the polynomial set equal to 0, I'm just going to quickly get into the 0 product property though. If I were to multiply these out, let's see here, I get a -x. This is a -x cubed, so that's going to give me a -x cubed. Very important for you to recognize that multiplication. And then this would give me another x cubed. Dot, 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 dot. So that's going to give me a, let's see, that's going to be a positive x to the 7th. So the end behavior for an odd power is going to be falls to the left, rises to the right. Now let's go and set each factor equal to 0. Now, again, you can set these as like the powers expanded here, because that's what I forgot to do. X minus 4. But also to kind of like save your time, like think about what is it you're doing here? Like here you're just dividing by negative, right? So therefore that's x is equal to 0. Here you're taking the cube root first and then you're doing the inverse operations. Here you're taking the cube root first. Like for instance here, like to solve this, you're going to need to take the cube root of both sides, which just gives us x minus 4 is equal to 0. And then you're going to add the 4 to both sides. So you can just avoid a lot of this. You're still going to want to have those powers in there or recognize that from the original problem. But a lot of times I just like to take the values inside of the factor and then set them equal to 0. For example, this value is x equals -2, right? You can use your inverse operations. I'm just trying to speed things up a little bit. So we have -2. That's going to have an odd degree, so it's going to cross. It is going to S-curve, but I'm just going to go with it odd. 0 is going to be, again, another odd one. And then we have at positive 4, 1, 2, 3, 4, is also going to odd. So let's kind of see if this works here. Okay, and just a reminder, at negative 2 and 3, those would technically have like a nice little S-curve, right? There you go. Make them look like a little bit better in that regard. But either way, you can see how those graphs would behave. And then at, oh, I'm sorry, that's at negative 2. Let's actually do it. Let's actually have a little fun with this. So at 0, it crosses. So here, S-curve, cross, and here would be like an S-curve. So you can kind of see how that cubic, you don't need to do that, or at least I don't expect my students to be able to do it, but I think it's nice to kind of remember that to help you out. All right, then the next one. Now we can find the end behavior, but before I go ahead and find the end behavior, I'm going to do something that's a little bit different here. Is I'm actually going to go ahead and rewrite this in linear factored form. So because I recognize some things here, I don't like this negative x written like that. So if I immediately write it like this, I recognize I can rewrite that as a negative x squared minus 4. I can factor out the negative, and then I can rewrite that as an x minus 2 times an x plus 2. Here, I can factor out the 2. Right? If you factor out a 2 in front of that expression. So far I've been able to factor out a negative and factor out a 2. And I'll show you why this is sometimes helpful if you get in a problem that you can do. So I can factor out a negative 2. That leaves me with a 2x plus 1, an x plus 2, and therefore an x minus 2 and a x plus 2. And the reason why this is, I think, helpful is you guys can recognize 2x plus 1, this x plus 2 is actually repeated. So squared times x minus 2. You might not have recognized that that is a repeated 0. But when I kind of show my work, you'll see how that would work, or how that came about. So anyways, let's look at our end behavior here. If we were to multiply this all out, this would be, let's see, 2, 3, and 4, and it's a negative, so it's going to fall down and fall down. Now, if you were just to take these factors and set them all equal to 0, that's fine. Like, you could just go about that just the way like I taught it. I recognize some things could be simplified, so that's why I kind of showed that step. But if you're to solve this, you're going to get x equals negative 1/2. Here you're going to get x is equal to a negative 2. And here you get x is equal to plus or minus 2. So what you notice is negative 2 repeats, right? It happens here and it happens here. Again, you can't write negative 2 twice as an x-intercept. That's why the multiplicity is so helpful. You recognize that if I simplified this, it actually, negative 2 actually repeats itself. So therefore, it's going to bounce at negative 2, not cross. At negative 1/2, let's just put that right there. It's going to have an odd multiplicity. And then at positive 2, you can see that it's going to also have a positive multiplicity. So let's see if this works here. So we go here, we bounce, we come across, and there you go. So that multiplicity, that odd multiplicity is very important, because if I didn't write that as repeating and I did that as crossing, there's no way you could start down here and start down there. That's why you had to have that bounce. All right, last but not least here for the graphing, we're going to have, so let's go ahead and multiply this out. So that's going to be 1/2. This would be x cubed, dot, dot, dot. This would be an x to the 4th, dot, dot, dot. And this would be a negative 3x plus 1. All right. So if I were to multiply all these, I would have a negative 3 times 1/2. So it's a negative 3/2. And x to the 3rd times x to the 4th times x is going to be 4x to the 8th. 7, 8. Oh, did I forget to change that? I did. Let's put this to a squared. Dang it. I knew I was going to do that. Forget that. There you go. So that's going to be negative 3/2 x to the 6, 7, 8, 9. Okay. So plus dot, 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 dot. All right. So as far as end behavior goes, We have rises to the left, falls to the right. We have, let's see, x plus 5. I can just take the factor, set them equal to 0. X plus 2 is equal to 0. And 1 minus 3x equals 0. So here I'm going to have x equals negative 5 with the multiplicity equal to 3. X equals negative 2 with the multiplicity equal to 4. And here I'm going to have x is equal to, let's see, subtract the 1 and then divide by negative 3. So it's a positive 1/3. And that's going to have a multiplicity equal to 2. Okay, so just remember, if it's an even multiplicity, it bounces. Odd multiplicity, it's going to cross. But at negative 5 here, 1, 2, 3, 4, 5, I could probably see that's going to follow this S curve or this, quintic kind of curve, but it's going to cross. At negative 2, it's definitely going to bounce because it has a multiplicity of 4. And then at 1/3, let's just put that like right there, then it's also going to have a multiplicity of 2, so it's going to bounce. All right, so let's go ahead and connect them. And boom. So you can see how that kind of exactly works. So hopefully you recognize as far as for the end behavior, just to find the end behavior, find the zeros or the x-intercepts, and then apply the multiplicity. All right, last but not least is the intermediate value theorem. Basically, what I just wanted to cover with students here was identifying if there's going to be zeros between the values. We'll get in more depth with this into calculus. But for basically on the intermediate value theorem, this kind of picture tells it all. Basically, all it's saying is as long as you have a continuous function, like a polynomial, which are all continuous, and you have an interval, a closed interval from a to b, then basically what that means is all the value, as long as c is a value with a and b, then f of c must exist. So like if I have a point here, like an x coordinate here, that means the y coordinate also must exist on that graph. And really what we're going to use that for is to determine if there's a zero. Like for instance, I have c here is at this x-intercept. So as long as a is negative and b is positive, right? You can see the y coordinate here is negative, the y coordinate over here is positive. Whenever you go from a negative to a positive or a positive to a negative, you have to cross the x-axis somewhere, right? It's impossible as long as the function is continuous for you to not cross the x-axis. Therefore, the value c has to exist. So let's go and take a look at this in terms of what types of questions you would have. So this one says, use the intermediate value theorem to show that there must be a real zero of the polynomial y equals x to the fourth minus 2x plus x minus 1 on the interval negative 2, 0. Now the important thing is I have no idea what this graph looks like. The only thing I need to know is if I have a polynomial, right, and it goes from here down to here, right? So let's say here's negative 2 and here's 0, whatever. Oh, that's a... So negative 2, and let's say 0 is down here, right? So here's negative 2, and obviously that's 0. So if I have a polynomial to go from here to here, if this y value is positive and this y value is negative, I had to somehow, to go from here to here, I had to cross the x-axis somehow, somewhere. The intermediate value theorem doesn't tell you where it crosses, it just tells you it has to exist. So basically, we need to figure out what the y coordinates are at negative 2 and 0. If we go from a positive to a negative or a negative to a positive, we know that 0 has to exist as a y value. And if 0 exists as a y value, we have a 0. So what we're going to do is I'm going to plug in negative 2. Okay, negative 2 raised to the fourth power. Any negative number raised an even number of times is going to be positive. That's going to be a positive 16. Negative 2 cubed is going to be odd, negative, so that's going to be negative 8. So negative 8 times negative 2 is going to be a positive 16. Minus 2 minus 1. So that gives us 29. Okay, so let's go and check on the y sub 0. Now this was nice. I don't really actually need to show my work here, but I'm going to, because every time you plug in 0 in for that x, they all go to 0, right? So you're just left with a negative 1. So even though these are like not technically are meant to be there, here the y value is 29. Here at 0, the y value is negative 1, right? So to go from a positive 29 to a negative 1, you had to cross the y-axis, and therefore you can see why by using the intermediate value theorem, or based on the intermediate value theorem, a 0 has to exist. So another one you can ask is, here's another polynomial. It's a continuous polynomial. Determine the interval that a 0 has to. It must be 0 based. Determine the interval. So again, let's just go ahead and check what each of these are. So I'm just going to plug in, this negative 1/2 or the interval into each one of these and see what that gives me. Whew. All right, so here this is going to give me a, let's see, that's going to give me a negative 1. Negative 1 minus 1, that's going to give me a negative 3/2. And 1 minus 1, that's going to give me a positive 3/2. So that negative times negative, that's going to give me a positive number. If you multiply those all across, that's going to give me a 9/4. So then let's go and check in y equals positive 1/2. So that's going to be a 2 times 1/2 times 1/2 minus 1 times 1 minus 1/2. So 2 times 1/2 is just going to be 1. 1/2 minus 1 is going to be a negative 1/2. And 1 minus 1/2 is going to give me a positive 1/2. So now you can see that that gives you a 1 minus 1/2, so that gives you a negative 1/4. It doesn't really matter what the value is. It matters the fact that you went from a positive value to a negative value. So therefore, you can see that this interval does work. Now, we can go ahead and play a little bit tricky here. Another way we can do is just plug in these values and just determine, is it going to be positive or negative? Because that's really what we're looking for. Is it going to be positive or is it going to be negative? So what I'm going to do is, if I plug in y of 1/2, well, y of 1/2 I already know that's going to be negative 1/4, right? So let's go and plug in y is equal to, or y of 3/2. So if I can just plug in y equals 3/2, that first times 2 is going to give me positive. 3/2 minus 1 is going to give me a positive. And I'll just write it in there so you can see. 2 times 3/2 times 3/2 minus 1 times 1 minus 3/2. Yeah, okay, that's fine. Again, that gives you 3, but really you just need to know it's positive or negative. Here, that's going to give me a 1/2, which is again positive. But then this is going to give me a negative 1/2, which is negative. So when you multiply those all out, you're going to get a negative 3/4. So again, since it's negative to negative, that does not prove that you had to cross the x-axis. You could have, but it doesn't prove that. And last but not least here in this one, rather than even plugging anything in, if I plug in 0, 0 gives me an x-intercept, right? So even though these are on a closed interval for negative 3/2 to 0, so therefore, since y of 0 gives me 0, then obviously that is going to be an x interval, or an x, that's going to be a 0 on that interval. So therefore, obviously, it's going to exist from right there. All right, ladies and gentlemen, so that is basically it for this lection. We covered, finding end behavior, being able to graph a polynomial, understanding the multiplicity, understanding the x-intercepts. So therefore, you can graph them. And then we finished off with using the intermediate value theorem. So hopefully this lesson was helpful for you. But if you do have any kind of questions or you want to reflect on items that made sense or that you're struggling with, then feel free to go ahead and shoot me down a question or reply in the comments, and I'll be happy to help you out. Cheers.